In the previous module, you learned that formation of tetrahedral and octahedral voids takes place when the constituent particles are arranged in a cubic close packing or hexagonal close packing. You also know that in a close packing, the number of octahedral voids formed is the same as the number of spheres or the constituent particles, while the number of tetrahedral voids is double the number of spheres. Let us now look at how the cations and the anions are placed in the close packing. Usually, the anions being larger in size form the basic crystal lattice, and the cations being smaller in size occupy the voids. A relatively small cation occupies the tetrahedral void, while a relatively bigger cation occupies the octahedral void. For example, sodium ions having size of 102 picometers occupy the octahedral voids in a sodium chloride lattice, and the zinc ions with size of 74 picometers occupy the tetrahedral voids in a zinc sulfide lattice. The fraction of octahedral or tetrahedral voids occupied in a given lattice depends upon the chemical formula of the compound. To have a better understanding of the concept, let us work on a few problems. In corundum, the oxide ions form the hexagonal close packing lattice, and the aluminium ions occupy 2/3 of the octahedral voids. What is the formula of the compound corundum? You already know that the number of octahedral sites in a cubic close packing is the same as the number of constituent particles. Now, if n oxide ions form the crystalline lattice, so the number of available octahedral sites is also n. But only 2/3 of n octahedral sites are occupied by the aluminium ions. This implies that the ratio of aluminium ions to the oxide ions in the lattice is 2/3:1. Thus, the whole number ratio of aluminium ions to the oxide ions is 2:3. The formula of corundum therefore becomes Al2O3. Let us solve one more problem. In a crystalline solid, anions B are arranged in a cubic close packing, and the cations A occupy 50% of the tetrahedral voids and 50% of the octahedral voids. What is the formula of the compound? Now anions B are arranged in cubic close packing. If n is the number of anions B, then the number of available tetrahedral voids is equal to 2n, and the number of available octahedral voids is n. Cations A occupy 50% of the octahedral voids. That is, cations A are present in n/2 octahedral voids. Also, cations A occupy 50% of the tetrahedral voids. That is, cations A are present in 2n/2 tetrahedral voids. The A is to B ratio thus becomes 3n/2:n. The simple whole number ratio of A is to B is 3:2. Thus, the formula becomes A3B2. Now let us try to locate the tetrahedral and the octahedral voids in the CCP or FCC structure. Consider a CCP or FCC unit cell. Subdivide this big cube into 8 small cubes as shown here. Now consider one small cube. A careful look shows that spheres are present at the alternate corners in this cube. when these spheres are joined, we get a tetrahedron, and the void thus generated is a tetrahedral void. As each small cube has one tetrahedral void, there are a total of 8 tetrahedral voids in a CCP or FCC unit cell. Also, you know that in a CCP or FCC unit cell, 4 atoms or ions are present per unit cell. Thus, the number of tetrahedral voids is 2 multiplied by 4. That is 8. Let us now locate an octahedral void in the CCP or FCC unit cell. A look at the body center of this unit cell shows that it is surrounded by 6 spheres at the center of each face. If we join these 6 spheres, we get an octahedron, and the void thus formed is an octahedral void. This octahedral void is not shared by any other unit cell and contributes fully to this unit. Further, octahedral voids are also present at the center of each edge. As you can see, each edge is shared by a total of 4 unit cells. It therefore contributes only 1/4 to each unit cell. Thus, the total number of octahedral voids present per unit cell comes out to be 4. This is same as the number of atoms or ions present in a CCP or FCC unit cell. You know that HCP stands for hexagonal close packing and CCP for cubic close packing arrangement of particles. Now let us study hexagonal close packing. In this arrangement, the spheres are closely packed in successive layers in the AB-AB type of arrangement, as shown here. Each unit cell has 17 spheres with radius r, and edge length of unit cell 2r. Among these, 12 spheres are at the corners of 2 hexagons, 2 spheres at the center of the 2 faces, above and below, and the remaining 3 in the middle of the unit cell as shown here. You can calculate how many atoms or spheres each HCP unit cell contributes. Each sphere at the corner of a unit cell is shared by 6 surrounding unit cells. So, the contribution of the corner atoms to a unit cell is 12 into 1 by 6, which is equal to 2. The contribution of the atoms at the 2 face centers is equal to 2 into 1 by 2, which is equal to 1. On the other hand, the contribution of the atoms inside the HCP unit cell is 3 into 1, which is equal to 3. So, the total contribution is 2 plus 1 plus 3, which is equal to 6. Note that the formula to calculate the volume of an HCP unit cell is base area into height. The base area of a hexagon is equal to 6 multiplied by root 3 upon 4 multiplied by 2r whole square. The height of a unit cell is equal to 4r multiplied by root 2 upon 3. So, the total volume of an HCP unit cell can be taken as 24 multiplied by root 2 multiplied by r cube. Let us now see the formula for packing fraction. It is the ratio of the volume occupied by spheres per unit cell to the volume of the unit cell. The volume of spheres in this unit cell is given by V sphere is equal to 6 multiplied by 4 upon 3 multiplied by pi multiplied by r cube, which is equal to 8 pi r cube. Substituting the volume terms in the packing fraction term and simplifying, the resultant value is 0.74, which is equal to 74%. Therefore, the packing efficiency in HCP arrangement is equal to 74%. Let's study cubic close packing now. Let the edge length of a unit cell be A is equal to 2R. And the radius of each sphere be R. In this arrangement, each unit cell has 8 spheres at the 8 corners and 6 spheres at the 6 face centers. So the contribution of the corner atoms to a unit cell is given by 8 into 1 upon 8, which is equal to 1. The contribution of the face center atoms is given by 6 into half, which is equal to 3. So the total contribution is 1 plus 3 is equal to 4. Let spheres A, B, and C lying on the unit cell form a right triangle, as shown here. Then, applying Pythagoras theorem, we get AC square is equal to AB square plus BC square. Therefore, AC square is equal to A square plus A square, which is equal to 2A square. Hence, AC is equal to root 2A. However, face diagonal AC in terms of edge length is AC is equal to 4R. Therefore, equating the two expressions for AC, we get 4R is equal to root 2A. Hence, R is equal to root 2 upon 4 multiplied by A as given here. Packing efficiency is the ratio of the volume occupied by the spheres per unit cell to the volume of a unit cell. The volume occupied by 4 spheres is given by 4 multiplied by 4 upon 3 multiplied by pi multiplied by R cube. This expression in terms of edge length A is 4 multiplied by 4 upon 3 multiplied by pi multiplied by root 2A upon 4 whole cube. Hence, the packing efficiency in CCP arrangement is 0.7406, which is equal to 74.06%. You know that BCC stands for Body-Centered Cubic Arrangement of Particles. Let's now study body-centered cubic arrangement. In this arrangement, the particles are present at the corners and the body center lattice points. Each unit cell has 9 spheres with radius R. The edge length of a unit cell is A is equal to 2R. Among these, 8 spheres are present at the corners, and 1 sphere at the body center of the unit cell, as shown here. You can calculate how many atoms or spheres each BCC unit cell contributes. Each sphere at the corner of a unit cell is shared by 8 surrounding unit cells. So the contribution of the corner atoms to a unit cell is 8 into 1 by 8, which is equal to 1. The contribution of the atom at the body center is equal to 1 into 1, which is equal to 1. So the total contribution of the atoms per unit cell is 1 plus 1, which is equal to 2. Consider points A, B and C on the unit cell which form a right-angled triangle. Therefore, on applying Pythagoras theorem, we can say AC square is equal to AB square plus BC square. Substituting the values, we get AC square is equal to A square plus A square, which is equal to 2A square. On the other hand, points A, C, and D lying on the unit cell form a right-angled triangle. Applying Pythagoras' theorem to these points, AD square is equal to AC square plus CD square. Hence, AD square is equal to 2A square plus A square, which is equal to 3A square. Therefore, AD is equal to root 3 into A. The body diagonal of a unit cell is AD is equal to 4R. Hence, equating the two expressions for AD, we can say that 4R is equal to root 3 into A. Hence, R becomes equal to root 3 upon 4 into A. Let us now see the formula for packing efficiency. It is the ratio of the volume occupied by spheres per unit cell to the volume of the unit cell. So, the volume of two spheres per unit cell is given by 2 into 4 upon 3 into pi into root 3 upon 4 into A whole cube. The volume of a unit cell is given by A cube. On substituting these expressions in the formula for packing efficiency and simplifying, we get 0.6805 or 68.05%. Therefore, the packing efficiency in a BCC arrangement is equal to 68.05%. Now let us study the simple cubic lattice arrangement. In this arrangement, the particles are present only at the corner lattice points of a unit cell. Each unit cell has 8 spheres with radius r. The edge length of a unit cell is A is equal to 2r. All these 8 spheres are present at the corners of a unit cell, as shown here. You can calculate how many atoms or spheres each simple cubic unit cell contributes. Each sphere at the corner of a unit cell is shared by 8 surrounding unit cells. So the contribution of the corner atoms to a unit cell is 8 into 1 by 8, which is equal to 1. This is the total contribution of the atoms to the unit cell. The volume of a sphere contributing to a unit cell is 4 upon 3 into pi into A upon 2 whole cube, while the volume of a unit cell is A cube. On substituting these expressions in the formula for packing efficiency and simplifying, we get 0.524 or 52.4%. Therefore, the packing efficiency in simple cubic arrangement is equal to 52.4%. By X-ray studies, we can determine the length of the edge of a cubic lattice. Knowing the type of crystal lattice that it has, we can determine the number of particles per unit cell. Once we know the two quantities, we can calculate the density of the crystal. Consider a cubic system with edge length A picometers, number of atoms per unit cell Z, and molar mass m. The volume of a cube is equal to A cube picometer cube, which is equal to A cube into 10 to the power minus 30 centimeter cube. You already know that density of a unit cell, ρ, is equal to mass of the unit cell divided by volume of the unit cell. Let this be equation 1. Mass of a unit cell is equal to number of atoms in the unit cell into mass of each atom. That is, Z into M, where M is equal to atomic mass by Avogadro's number. Substituting the values in equation 1, we get ρ is equal to Z into M divided by A cube into 10 to the power minus 30 into Avogadro's number grams per centimeter cube. Let's work out a problem based on this concept. Calculate the density of silver by using the data given. H length of its unit cell is 408 picometers and molar mass is 108 grams per mole. Silver forms a CCP lattice. You know that ρ is equal to Z into M upon A cube into 10 to the power minus 30 into Avogadro's number grams per cubic centimeter. For a CCP lattice, which is equivalent to an FCC lattice, Z is equal to 4. By substituting the values, we get the density of silver as 10.5 grams per cubic centimeter. If the constituent particles, such as atoms, ions, or molecules, in a solid crystal are arranged in a regular fashion, then the crystal is said to be an ideal or perfect crystal. However, no crystal in the universe is perfect. Almost all the crystals encountered in practice suffer from defects. This happens when the crystallization process occurs at a fast or moderate rate. In order to avoid these defects, the process of crystallization is conducted at an extremely slow rate. However, even the crystals so obtained are also not free from defects. These defects in solids are broadly classified into point defects and line defects. Point defects are the irregularities or deviations from the ideal arrangement around a point or an atom in a crystalline substance. These may arise in a crystal due to one of several reasons: the absence of a constituent particle, the presence of a foreign particle at the lattice site, the presence of a foreign particle at the interstitial site, the displacement of a particle to the interstitial site. Point defects are classified into 3 types, namely stoichiometric defects, non-stoichiometric defects, and impurity defects. Let's first learn about stoichiometric defects. A stoichiometric defect is a defect by which there is no disturbance in the stoichiometry of the solid. These are also called intrinsic or thermodynamic defects. Stoichiometric defects are further classified into vacancy defects and interstitial defects. The defect in which a constituent particle is missing from the crystal lattice is known as a vacancy defect. This defect develops when a substance is heated you can clearly observe from this figure that some of the constituent particles are missing from the crystal lattice. As a result, some vacancies are created. The major consequence of a vacancy defect is that the density of the substance decreases. On the other hand, an interstitial defect arises when some of the constituent particles occupy the interstitial sites in a crystal lattice. From the figure, it is evident that some constituent particles occupy the interstitial sites in a crystal lattice. As a result of this defect, the density of the substance increases. This holds good only for non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than a simple vacancy or interstitial defects, ionic solids show Frankl and Schottky defects. Now let us learn about Frankl defects and Schottky defects. A Frankl defect is caused if some of the ions of a lattice occupy the interstitial sites by leaving a corresponding number of normal lattice sites vacant. You can see this from the figure here. This creates a vacancy defect at the original site and an interstitial defect at its new location. A Frankl defect is also known as a dislocation defect. It does not influence the density of the substance. This type of defect occurs in compounds with ions of different sizes. Since cations are smaller than anions, cations can easily fit into the vacant spaces in the lattice. For example, in a silver chloride crystal, an Ag+ ion occupies an interstitial site by leaving a vacancy at the original site. Zinc sulfide, silver bromide, and silver iodide are other examples that have Frankl defects. A Schottky defect is caused if some of the lattice sites remain unoccupied. The number of missing positive ions is equal to the number of missing negative ions, and thus the crystal remains electrically neutral. Unlike a Frankl defect, a Schottky defect causes a decrease in the density of a substance. This defect is commonly observed in compounds in which the cations and the anions are of almost the same size. Sodium chloride, potassium chloride, and cesium chloride are well-known examples of this defect. The number of Schottky defect in ionic solids is quite significant. For example, in a crystal of sodium chloride, 1 million Schottky pairs per cubic centimeter are noticed. You are already aware that point defects are of three types, namely stoichiometric defects, impurity defects, and non-stoichiometric defects. In the previous module, you studied stoichiometric defects. You will learn about the other two defects in this module. Let's start with impurity defects. You already know that it is almost impossible to obtain a perfectly pure substance. Purification is a costly process. In general, analytical, reagent-grade chemicals are of high purity. Yet, few of them are more than 99.9% pure. This means that a foreign atom, ion, or molecule is present in the crystal. In such a case, we can say that the crystal has an impurity defect. For example, during the crystallization of molten sodium chloride, if it contains a small quantity of strontium chloride, then some of the sites of sodium plus ions are occupied by strontium plus 2 ions. Each strontium plus 2 ion replaces 2 sodium plus ions. Strontium plus 2 occupies the site of one sodium ion, and the other site remains vacant, which results in the creation of cationic vacancies in the crystal. The number of cationic vacancies is the same as the number of strontium plus 2 ions present in the crystal. Another similar example is the solid solution of cadmium chloride and silver chloride. The defects that we discussed so far do not disturb the stoichiometry of crystalline substances. However, non-stoichiometric defects affect the stoichiometry of crystalline substances. Let's first define a non-stoichiometric defect. The defect that causes the ratio of the number of cations to anions to be different from that indicated by the ideal chemical formula is known as a non-stoichiometric defect. Non-stoichiometric defects are of two types: metal excess defects and metal deficiency defects. Let's first discuss metal excess defects. A metal excess defect may arise in crystals due to anionic vacancies or the presence of extra cations at the interstitial sites. Metal excess defects that occur due to anionic vacancies can be illustrated by taking sodium chloride as an example. When crystals of sodium chloride are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the sodium chloride crystal. The Cl- ions present in the sodium chloride crystals diffuse to the surface of the crystal and combine with the sodium atoms present there to give sodium chloride. This happens because sodium atoms lose electrons to form sodium ions. The electrons so released diffuse into the crystal and occupy the anionic sites created by the diffusion of the chloride ions. As a result, the crystal now has an excess of sodium ions. The anionic sites occupied by unpaired electrons are called F centers. Here, F stands for Farbenzenter, a German word that means color center. The anionic sites occupied by unpaired electrons are called so because they impart color to the crystal. For example, excess of sodium makes sodium chloride yellow. Excess of lithium makes lithium chloride pink. And an excess of potassium makes potassium chloride violet. The reason for this phenomenon is the excitation of the electrons present at the anionic sites of the crystal when they absorb energy from the visible light falling on it. Now let's see how a metal excess defect arises due to the presence of extra cations at the interstitial sites, with zinc oxide as an example. Zinc oxide is a white solid at room temperature. On heating, it loses oxygen and turns yellow. Now there is an excess of zinc in the crystal and its formula changes from ZnO to Zn1 plus XO. The excess zinc 2 plus ions move to the interstitial sites and the electrons to the neighboring interstitial sites. The other class of non-stoichiometric defect is metal deficiency defect. This defect may arise due to cationic vacancies. It occurs when positive ions are missing from its crystal lattice. A typical example of this type is FeO, which is mostly found with a composition of Fe 0.95O. It may actually range from Fe 0.93O to Fe 0.96O. In crystals of FeO, some Fe2 plus cations are missing, and electrical neutrality is maintained by the presence of the required number of Fe3 plus ions. Iron sulfide, nickel oxide, and titanium oxide are other examples that have this defect. Line defects are the irregularities or deviations from the ideal arrangement in entire rows of lattice points. These arise mostly due to the misalignment of particles or the presence of vacancies along a line. Electrical conductivities of solids are spread over the widest range of any physical property, extending over 27 orders of magnitude, ranging from 10 to the power minus 20 to 10 to the power 7 ohm inverse meter inverse. On the basis of their electrical conductivity values, solids can be classified into three categories: conductors, insulators, and semiconductors. Conductors have extremely high conductivity values, ranging from 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. Insulators have extremely low conductivities, ranging between 10 to the power minus 20 and 10 to the power minus 10 ohm inverse meter inverse. Semiconductors have conductivities in the intermediate range, from 10 to the power minus 6 to 10 to the power 4 ohm inverse meter inverse. Let's first study conductors in detail. Depending upon the mode of conduction, conductors can be classified into two types: metallic conductors and electrolytic conductors. In metallic conductors, the conduction is due to the movement of electrons. They are also referred to as electronic conductors. Metals belong to this category and conduct electricity without undergoing any change. On the other hand, in electrolytic conductors, the flow of electricity is due to the presence of ions. This type of conductors conduct electricity only in their molten and aqueous states. In solid state, they conduct electricity to a very small extent, and that too due to the presence of imperfections in them. Electrolytes like sodium chloride and potassium chloride are electrolytic conductors. The conductivity of metals depends upon the number of electrons present in the valence shell of their atomic orbitals. The electrons of a single isolated atom occupy atomic orbitals that form a discrete set of energy levels. When the atoms come close together, the overlap between their atomic orbitals results in the formation of molecular orbitals. When a large number of atoms come together to form a solid, the number of molecular orbitals becomes exceedingly large. Consequently, the difference in the energy between them becomes very small. Thus, in solids, the energy levels form continuous bands of energy rather than discrete levels of energy. This leads to a band of molecular orbitals of almost a continuum of energy. The band that holds the valence electrons is called the valence band. The other band, which is slightly higher in energy and is formed by the overlap of atomic orbitals, is called the conduction band. In metals, the valence band overlaps the conduction band. This results in easy flow of electrons under an applied electric field, and the metal shows conductivity. In insulators, as you can see, the electrons in the valence band are separated by a large gap from the conduction band. The gap region is called the forbidden zone. This gap is so large that enough energy is not available under normal conditions to promote electrons from the valence band to the conduction band. Hence, the solid behaves as an insulator. In semiconductors, the energy gap between the valence band and the conduction band is smaller than in insulators. The thermal energy available under ordinary conditions is sufficient to excite some electrons from the valence band to the conduction band. Thus, only a small amount of current can flow through them. Thermal energy is one of the main mechanisms for electrons to be excited to the conduction band. Therefore, the conductivity of semiconductors depends strongly on the temperature of the material. At absolute zero, semiconductors are perfect insulators. But at room temperature, there is enough thermal energy to allow the occasional electron to jump. And this gives the semiconductor limited conductivity. Semiconductors can be classified into two broad categories. First, there are intrinsic semiconductors. These are composed of only one kind of material. Silicon and germanium are two examples of intrinsic semiconductors. They are also called undoped semiconductors. The other type of semiconductor is the extrinsic semiconductor. These are made of intrinsic semiconductors to which other substances have been added to alter their properties. With a small energy gap in the semiconductors, the presence of a small percentage of a doping material can increase the conductivity dramatically. You are already aware that the electrical conductivity of semiconductors is very low. The addition of a small percentage of foreign atoms to a regular crystal lattice of an intrinsic semiconductor like silicon or germanium, produces dramatic changes in its electrical properties. Such impurities introduce electronic defects in the semiconductor and produce an N-type or P-type semiconductor. Let us first look at N-type semiconductors. In an N-type semiconductor, the doping atom usually has one more valence electron than the host. The addition of a pentavalent impurity, such as antimony, arsenic, or phosphorus, contributes free electrons to the silicon or germanium lattice. This produces an N-type semiconductor. The free electrons contributed by the pentavalent impurity are responsible for conduction of electricity in an N-type semiconductor. Let us now study P-type semiconductors. The addition of a trivalent impurity, such as boron, aluminium, or gallium, to an intrinsic semiconductor creates deficiencies of valence electrons. As you can see here, one electron is missing from one of the 4 covalent bonds in the silicon crystal lattice. These are called holes. The dopant atom can accept an electron from the covalent bond of the neighboring atom to complete the 4th bond. This causes the neighboring atom to lose a bond electron and results in the formation of a hole at the neighboring site. This shift in electrons from the neighboring site to the hole continues. It is important to note that holes are the majority carriers, while electrons are the minority carriers in P-type semiconductors. Also, the direction of conduction of electricity is opposite to the movement of holes in P-type semiconductors. Let us now take a quick look at the applications of P and N-type semiconductors. The most important application is in a p-n junction diode. Here, a P-type and an N-type semiconductor are brought together in close contact, creating a depletion region. In the depletion region, P-type holes recombine with N-type free electrons, allowing current to pass. In a light-emitting diode, LED, this current produces light. A photodiode converts light into electricity. The common, traditional solar cell used to generate solar power is actually a large area photodiode. It is important to note that in a diode, current can flow in one direction only, but not in the other, and this forms the basis of digital electronics. One of the most popular applications of the diode is in rectifiers. Rectification is the conversion of alternating current into direct current. A rectifier is a device that allows electrons to flow only in one direction. Another application of N and P semiconductors is in the transistor. It is a semiconductor device used to amplify current. There are 2 types of standard transistors, NPN and PNP. The letters refer to the layers of semiconductor material used to make the transistor. A large variety of compound semiconductors, composed of elements from 2 different groups of the periodic table, such as 13, 15 and 12, 16, are widely used in communication devices. These semiconductors simulate an average valence of 4 electrons, as in germanium and silicon. Some typical compounds of groups 13-15, like indium antimonide, aluminium phosphide, and gallium arsenide, have revolutionized the design of semiconductor devices. Gallium arsenide has some electronic properties that are superior to those of silicon, which makes it an excellent material for space electronics. Group 12-16 semiconductors are materials whose cations are from group 12 and anions are from group 16 in the periodic table. Zinc sulfide, cadmium sulfide, cadmium selenide, and mercuric telluride are examples of groups 12-16 compounds that find applications ranging from biomedicine to solar cell technology. Transition metal oxides are another category of substances that show diverse electrical properties, ranging from strongly metallic to insulating. Oxides like titanium 2 oxide, chromium 4 oxide, and rhenium 6 oxide behave like metals. Rhenium 6 oxide can be compared to metallic copper in conductivity and appearance. Oxides like titanium 4 oxide, vanadium 6 oxide, and many metal 2 oxides behave as insulators. For certain metal oxides like titanium 3 oxide, vanadium 3 oxide, and vanadium 4 oxide, there is a transition in electrical property from metallic to insulators at a certain temperature. Every substance is associated with some magnetic character. The magnetic property of a substance is due to the presence of electrons. Each electron in an atom is regarded a micromagnet. The magnetic moment of an electron originates from 2 types of motions, known as spin-angular motion and orbital angular motion. Thus, every electron has a permanent spin magnetic moment and an orbital magnetic moment associated with it. The values of magnetic moment are very small and are measured in units called Bohr magneton. 1 Bohr magneton is equal to 9.27 into 10 to the power minus 24 ampere meter square. Based on magnetic properties of materials, they are classified into 5 categories, namely diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Let's discuss the properties of these materials, starting with diamagnetic materials. Diamagnetic materials are materials that are repelled by magnets. When a bar of diamagnetic material is placed in a non-uniform external magnetic field, it tends to move from a region of strong magnetic field to a region of weaker magnetic field. Diamagnetism is shown by substances in which all the electrons are paired and there are no unpaired electrons. Although diamagnetism is present in all materials, its effect is very weak in most of them. Some examples of diamagnetic substances are water, sodium chloride, and benzene. Let's look at paramagnetic materials. Paramagnetic materials are materials that are weakly attracted by magnets. When a bar of paramagnetic material is placed in a non-uniform external magnetic field, it tends to move from a region of weak magnetic field to a region of stronger magnetic field. Paramagnetism is due to the presence of one or more unpaired electrons which are attracted by the magnetic field. Some examples of paramagnetic materials are iron +3, copper +2, and chromium +3. Let us now discuss ferromagnetic materials. Ferromagnetic materials are materials that are strongly attracted by magnets. When a bar of ferromagnetic material is placed in a non-uniform external magnetic field, it has a strong tendency to move from a region of weak magnetic field to a region of stronger magnetic field. In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. Thus, each domain acts as a tiny magnet. When the ferromagnetic substance is placed in a magnetic field, all the domains get oriented in the direction of the magnetic field. Iron, cobalt, nickel, and gadolinium are some examples of ferromagnetic materials. Let's now discuss antiferromagnetic substances. These substances have the same domain structure as ferromagnetic substances. However, their domains are oppositely oriented and cancel out each other's magnetic moments. Manganese dioxide is an example of an antiferromagnetic substance. Finally, let's look at ferrimagnetic materials. Ferrimagnetism is observed when the magnetic moments of the domains in a substance are aligned in parallel and anti-parallel directions in unequal numbers. These substances are attracted more weakly by a magnetic field as compared to ferromagnetic substances. Magnetite and ferrites like MgFe2O4 and ZnFe2O4 are some substances that show ferrimagnetism.